In this video, we're going to use what we learned about Kw, the equilibrium constant for the ionization of water, and find a very interesting relationship that Kw has with Ka and Kb. Which begs the question, what are Ka and Kb? Well, recall that whenever we have an acid ionization reaction, the Keq constant for that reaction is called Ka. A is for acid. And for a base ionization, Keq is simply called Kb because it is a base ionization. So if we write out the ionization reaction for acetic acid, we start with the acid form, CH3COOH, reacting with water, where water is going to use the negative pole on oxygen to pull off the easily ionizable hydrogen, and because acetic acid loses an H+, this is functioning as our acid, and water is functioning as our base. So the conjugate base that we're going to get after acetic acid ionizes is simply CH3COO-, which is acetate, and this is our conjugate base, and we can see that because it's missing the extra ionizable hydrogen here, while conversely, because water has gained this hydrogen here, it's going to be H3O+ in the products, and this is the conjugate acid that corresponds with water that acted as our base. Now, if we want to write the Ka expression, remember that this is constructed the same way as we do all Keq expressions. Water is not going to appear in the reaction because it is acting as the lone solvent, and because the concentration of liquids is defined as being constant. So the numerator of our Ka expression is going to be the concentration of acetate times the concentration of hydronium divided by the concentration of acetic acid. Now, frequently in textbooks and as generalized examples, rather than using a specific conjugate acid-base pair, we can simply write this out as a generalized acid ionization reaction, where we represent the acid as being Ha, with H being the easily removable hydrogen, and A- being the conjugate base form of the acid after the hydrogen has been lost. So our generalized Ka expression would look something like concentration of A-, the conjugate base, times the concentration of H3O+, divided by the concentration of our acid, Ha. Now, we can do the same thing for constructing a base ionization reaction, but we're not just going to write the reverse reaction here. We're actually going to use acetate, the conjugate base, as its own starting reactant. So if we do the ionization reaction where we take acetate and react it with water directly, we know that acetate is going to act as a base because it's going to use its negative charge to pull one of the hydrogens off of water in order to give us the acid form back, acetic acid, and because water has lost a hydrogen here, we would end up with OH-, therefore showing us that this is a base reaction here. So if we wanted to represent this in a generalized form, remember that we're starting with the conjugate base to start, A-, and then this is going to ionize with water in order to get us the acid back. So our specified Kb expression for the ionization reaction of acetic acid is going to look like this, where we have the concentration of acetic acid times the concentration of OH- divided by the concentration of our conjugate base, like so. And if we were to write this as a generalized reaction here, we would have the concentration of our acid form of the conjugate acid-base pair times the concentration of OH- divided by the concentration of conjugate base. In either case, what I'm about to show you will work with a specific Ka-Kb pair or with a generalized form here. Now, for the sake of argument, what we're going to do is take the Ka equilibrium expression and the Kb equilibrium expression for the conjugate base and multiply the two together in order to see what we get. So if we take our Ka expression, concentration of acetic acid, acetate, multiplied by the concentration of H3O plus, divided by the concentration of acetic acid, and if we multiply that to our Kb expression, which is concentration of acetic acid times concentration of hydroxide divided by the concentration of the conjugate base, which is acetate, we see here that our concentrations of the acid and of the conjugate base appear in both the numerator and the denominator, which means that each of them cancels each other out. And if you try this with the generalized equations here, you'll find that we get exactly the same result. And if we simply look at what's left over, which is concentration of hydronium times the concentration of hydroxide, this is equal to Kw. So what we have just discovered is that the Ka and Kb of a conjugate acid-base pair are directly related to each other, because when we multiply the Ka of the acid and the Kb of the conjugate base together, you will always get Kw, and the algebra shows that this is the case. Now, because we know the value of Kw at atmospheric temperature, 1.0 times 10 to the negative 14, this allows us to mathematically calculate one of Ka or Kb, provided that we know the other. So, for example, if we actually wanted to find out the numerical value of the Kb of NH3, we could do that assuming that we know the Ka value of its conjugate acid. And the conjugate acid of NH3, remember that this is the base, so to find the conjugate acid, all we would need to do is add a hydrogen to it, which would happen to be NH4. Now, how do we find the actual Ka value? Well, we need to look at a data table, and whenever it comes to acid-base equilibria, most of the time, data tables will list off either Ka or Kb, but not both, because we don't actually need both because of this relationship between Ka, Kb, and Kw. So if we scroll down here, we can find that the Ka value of NH4's acid ionization is 5.6 times 10 to the negative 10. So all we would need to do in order to calculate the Kb is, if we know that Ka times Kb is equal to Kw, and if we know that Kw is equal to 1.0 times 10 to the negative 14, all that we would need to do to find Kb is divide Kw by Ka, which means that our value of Kb would be equal to 1.0 times 10 to the negative 14, that's what Kw is, divided by the Ka, sorry, I've made a slight mistake here, divided by the Ka of the conjugate acid, which, as we saw in the data table, is 1.8 times 10 to the negative 10. I'm not going to bother putting this into a calculator because as a fraction, this is the most accurate representation. But using this, it allows us to find the Kb of a base, assuming that we know the Ka value of an acid. And if we know the Ka and Kb values of acids and bases, it allows us to actually do equilibrium calculations, which is the topic of the next series of videos.